Hello everyone and welcome to our module on Wigger's diagram. Shown on the screen is an example of Wigger's diagram. This is a diagram that shows different events that occur during the cardiac cycle, all correlated to one another. So on Wigger's diagram, time is always along the x-axis, and what we're showing is one cardiac cycle, in other words, one iteration of systole and diastole as the heart goes through the cardiac cycle. And you can see the different things that are happening during the cardiac cycle shown on the diagram. So at the bottom is an EKG tracing, and it shows the QRS complex and the T wave. But the beauty of Wigger's diagram is you can see how things like the QRS complex match up with other events like all the things shown also on Wigger's diagram. So for example, here we have changes in venous pressure, which I talk about in a separate video. Here we have heart sounds. Here we have the left ventricular volume, which goes down as the left ventricular cavity empties and then goes up as it fills. And then up at the top of Wigger's diagram, you usually see the pressures in three different parts of the body. First of all, the left atrial pressure, which is always the lowest. That's this dotted green line you see here. Then the left ventricular pressure, and then finally at the top, the aortic pressure. And so once again, the beauty of Wigger's diagram and the reason it's been taught in physiology courses for decades and decades is because it correlates all these different parts of the cardiac cycle to one another, so you can see things that are happening at the same time. Let's start by zooming in on the left ventricular volume portion of the cardiac cycle. So the QRS complex always represents the start of systole. That's when the myocytes in the left ventricle depolarize and start to contract. Notice that initially when that happens, there's this brief period where volume doesn't change. This is called isovolumic contraction. And what's happening is the ventricle is contracting, but the aortic valve hasn't opened yet, so blood can't leave the ventricle. Instead, what it's doing by contracting is simply building pressure. Now, eventually that pressure in the left ventricle gets high enough to open the aortic valve. That's what happens right here. And when that happens, blood starts to leave the left ventricular chamber and go out into the aorta, and that's why volume is falling on this graph here. When we reach a point about right here, the aortic valve closes, and therefore volume can't change anymore. At this point in time, the ventricle is relaxing. This is diastole, but the mitral valve hasn't opened yet. So we have this brief period here where volume doesn't change. That's called isovolumic relaxation. It's part of diastole. And then finally, the mitral valve opens, and then we get what you've got right here, which is filling of the left ventricular volume, once again to a high level. And then this can go on over and over again as cardiac cycles repeat themselves. And so if we go back to Wigger's diagram, remember that I told you that the QRS complex represents when systole begins and the ventricle starts to contract. That's this point up here we just talked about on the LV volume curve, the beginning of this portion called isovolumic contraction. And you can see that this point in time on Wigger's diagram is associated with S1. And that should make sense to you because when the ventricle contracts, it closes the mitral valve, and the mitral valve closing is a component of S1. And so that's why you see the heart sound right here lining up with these other events we've just talked about. Now let's go back to the three pressure curves at the top of Wigger's diagram. So the dotted line is left atrial pressure, and that's always the one that's low along the bottom because pressure in the left atrium is always relatively low. A normal left atrial pressure is about 10 millimeters or so, much lower than your blood pressure of 120/80. So the curve for left atrial pressure is always down at the bottom of these three curves at the top of Wigger's diagram. At the top, we have the aortic pressure. And as you may know, aortic pressure in a person with normal blood pressure goes down to a low point of about 80 millimeters of mercury, and then it rises to a high point of about 120 millimeters of mercury. And we call these the diastolic and systolic blood pressures. The third curve for pressure is the left ventricular pressure. And that one is always the biggest curve because the left ventricular pressure has to get very low. It has to get lower than left atrial pressure in order for the ventricle to fill and for the mitral valve to open. But then the left ventricular pressure has to climb up and become higher than the aortic pressure in order to open the aortic valve. So I've cleared away my ink so I can show you some important points on these three curves. So right here where left ventricular pressure climbs to become greater than left atrial pressure, that's when the mitral valve closes. The left ventricular pressure gets above the left atrial pressure. That's because the left ventricle is starting to squeeze the blood in the chamber. It drives up the pressure, and once it's higher than the left atrial pressure, it will close the mitral valve. Then we have this period where pressure is rising, but the aortic valve isn't open yet. So this is that period we just talked about earlier, isovolumic contraction. Pressure's rising in the left ventricle, but the mitral valve is closed and the aortic valve hasn't opened yet, so no valves are open and no volume can leave the chamber. The only thing that's happening is pressure is rising. Now eventually we get to this point right here where left ventricular pressure becomes slightly higher than aortic pressure. At that point in time, the aortic valve opens, and now we see that blood starts to move out into the aorta, raising the pressure in the aorta along with the pressure in the left ventricle. Basically, the two pressures are going up together because the aortic valve is open. Now at this point in time right here, left ventricular pressure starts to fall. The left ventricle has stopped contracting and it's starting to relax. And when left ventricular pressure gets lower than aortic pressure, that's when the aortic valve closes. And then finally, you have this point down here where left ventricular pressure falls so that it's lower than left atrial pressure. And when that happens, the mitral valve is going to open. And so what you can see here is I've pointed out the 4 points where the mitral valve opens and closes and the aortic valve opens and closes. And you should be able to recognize those points on Wigger's diagram. And so I've cleared away my ink again so I can show you another important point. Everything from this point here where the mitral valve closes until this point right here where the aortic valve closes, this is all systole in here. All the events that occur in this period of time are systolic events. And then everything after this line until the next cardiac cycle represents diastole. And then going back to Wigger's diagram once again, you should be able to identify where the mitral valve closes right here, where the aortic valve opens here, where the aortic valve closes here, and where the mitral valve opens here. And you should know that everything from this point here to this point here is going to represent systole, and then things over here are going to represent diastole. And then when you know that, you can correlate events at the top of Wigger's diagram to all sorts of things down at the bottom, like EKG findings, venous pressure changes, and heart sounds. So I'll finish this video by going through a couple of examples of pathologic conditions that you can identify using the tracings at the top of Wigger's diagram. So once again, I've shown normal tracings from the top of Wigger's diagram on the left. That's right here. The dotted green line is the left atrium. This line here is the left ventricular pressure. And at the top, we have the aortic pressure. On the right side of the screen is an example of a diseased heart. We have the left atrial pressure in blue along the bottom. This red line represents the aortic pressure. And then this green line represents the left ventricular pressure. And so the major finding here is that during this period of time when the aortic valve is open until it closes, we have a much higher pressure in the left ventricle compared to the aorta. That's very abnormal. Usually those pressures mirror each other and they go up and down together, but here the left ventricular pressure is much higher than the aortic pressure. And that's a classic finding that you see in aortic stenosis. So the reason for this pressure difference here, it's sometimes called a pressure gradient. The reason there's a difference between the LV systolic pressure and the aortic systolic pressure is because that additional pressure inside the left ventricle is required to push open that stiff aortic valve and push blood past the resistance of that stiff aortic valve. And so here we've got another example of a diseased heart on the right side of the screen. Once again, the red line is the aortic pressure, the green line is the left ventricular pressure, and the blue line is the left atrial pressure. Well, remember at this point in time, the mitral valve opens, and at this point in time, the mitral valve closes. So this period in here is diastole. That's when the left ventricle is filling. And because the mitral valve is open, so there's communication between the left atrium and left ventricle, usually those two pressures are basically the same, like what you see over here in the normal heart. But in this case, we have another pressure difference. We have another gradient, this gray area in here. Something is requiring the left atrial pressure to get higher in order to open the mitral valve and push blood into the left ventricle. And that something is mitral stenosis. So the finding in mitral stenosis is a difference between the left atrial pressure and the left ventricular pressure during the period of diastolic filling when the mitral valve is open. Okay, so now we've got another diseased heart on the right side of the screen, and in this case, the major finding has to do with the left atrial pressure, the blue line right here. So normally, left atrial pressure climbs very slowly as blood fills the left atrium from the pulmonary veins. But in this diseased heart, left atrial pressure is rising much more rapidly than normal. And that's what happens when you have mitral regurgitation. So as the ventricle is contracting and pushing blood out into the aorta, it's also pushing blood back into the left atrium through the leaky mitral valve. And that causes the left atrial pressure to rise much higher than it normally otherwise would. Okay, and then our final example of a diseased heart I'll show you is this example on the right side of the screen here. In this case, the major finding has to do with the aortic pressure tracing, the red line. So normally, blood volume slowly moves out of the aorta, causing the pressure to slowly fall in diastole until the next cycle of systole, where the volume goes back up again and the pressure rises. But in this red line on the right, in this diseased heart, blood pressure in the aorta is falling much more rapidly compared to normal. That's what happens when there's an unusual way for blood to leave the arterial system, one that's not normally present. And in this case, it represents aortic regurgitation. So because blood can leak back out of the aorta into the left ventricle, the pressure falls much more rapidly than it normally would in a normal heart. That's what you see in aortic regurgitation. A classic finding in aortic regurgitation is a low diastolic blood pressure, and that's what you've got here, much lower compared to normal. Another classic finding in aortic regurgitation is a wide pulse pressure. The pulse pressure is the difference between the diastolic and the systolic blood pressure. And you can see that it's much wider in this diseased heart on the right compared to what it would be in the normal heart on the left. Another classic finding of aortic regurgitation. And that concludes our module on Wigger's diagram.